Hey folks, this is another way to do a simulation. The other day we did a simulation using R, and you had to do an awful lot of work in order to make R produce a histogram. You had to do a lot of writing of code to get samples and that sort of thing, and some of the code was challenging to understand. So, today we're going to look at this little program that should make things a little bit easier. But I'm going to walk you through real quick how it works. So, this is a candy machine that is full of Reese's Pieces, and it has all different colors of Reese's Pieces, just like Reese's Pieces come in. I had to go back for a second and double check to see whether Reese's Pieces still actually exist. I didn't even know. Anyways, apparently they're still out there. Hopefully you've had them. Anyways, Reese's Pieces come in a variety of colors. I think there's like brown, orange, yellow, at least those three colors. Anyways, what's interesting about looking at statistical data, I'm going to repeat something that I've said before, is that usually when we're trying to summarize a bunch of data, there's two ways that we quantify. One is we will look at the average or the mean of the data, and another way is to find the proportion of the data. And typically, if we have quantitative data, we look at the mean, and if we have categorical data, we'll use proportions. Well, anyways, with this machine, what we're going to look at is the proportion of orange candies that we get, orange candies. What is a proportion again? A proportion is just a fraction or a percent of the things that you get. So for instance, if we asked a bunch of people which they preferred, Coke or Pepsi, and they said, and 55% of them said Coke, that 55% would be the proportion of people that prefer Coke over Pepsi. Now, the thing that's kind of interesting is when you go to find a proportion, it doesn't have to be just two things that you're comparing. In this particular case, we're going to look at the orange candies, but there are multiple other colors. But the only thing we care about is what is the proportion of orange candies. Now, there's a couple of parameters that we can change here, and one of them is the probability of getting orange. We did this when we were playing around with R the other day. Let's see here, we tried various values for the probability of getting one candidate or another. I'm going to go ahead and set this to 0.6, so it's not 50-50. There will be a 60% chance of getting orange. Now, in each of my samples, I have the sample size is 25, and that's fine. You can make the sample size bigger or smaller, but 25 is a pretty good size for statistics purpose. In other words, if you had to go sample your fellow, students at the school and you wanted to find out something, asking 25 students would give you, as long as you randomly chose those 25 students and you did not bias them with your question or whatever, 25 is a reasonable sample size. Of course, if we could get larger, we'd have a more accurate reading. Anyways, the other thing is how many samples will we take? So we may fool with that number as well. Also, what statistic are we interested in keeping track of? We could keep track of the number of orange pieces we get or the proportion of orange. So we're going to choose proportion of orange. So again, if you're taking notes right now, and you probably should be, you're going to change the probability to some number other than 0.5. And you're going to change and somewhere around the middle would be good, somewhere between 0.4, 0.6. If we get too far to one end or the other, then our histogram will move around and it'll look skewed even if it's not. So anyways, and again, I'm only telling you this for our purpose of learning and experimentation. In the real world, if we believe something has a 10% probability, you go with 10% probability. Anyways, so make a note that you'll change probability of orange, you'll change number of orange to proportion of orange, and then we'll go ahead and we'll begin to draw samples. And one of the cool things about this program is that after the samples are drawn, you get a dot on your histogram that indicates what the what the statistic was for. In this case, I think it is a statistic because it has p with a little hat over the top. That is the way we talk about a proportion when we're talking about a sample or a statistic. Statistics go with samples. Parameters go with populations. So anyways, we got a proportion of 0.52. Here it is up here, and that's why the dot goes down there. And then if I go and draw another sample, we'll get another proportion of oranges, of orange. So again, this 0.52 is the percentage of orange Reese's Pieces that I got compared to the entire amount that I got from that 25 sample candies. Okay, so coincidence that it also happened to be 0.52. Let's go ahead and draw another sample. Okay, so this time we got 0.6. So even though we set the probability, oh, I'm sorry. When you set the probability of orange to be 0.6, what it means is that we are setting up this candy machine so that 60% of the Reese's Pieces are orange. When we do now you can see there's many candies in this candy machine, way more than 25. When we pull down a sample, we're not expecting to get 60% every single time. In this case we did, but it's just a coincidence. We're expecting to get various results. And the goal here is we're trying to learn about how sampling works. And what we want to know is if we just happen to draw a random sample from a population, is it possible that that sample represents the actual population? In other words, if we have a political survey and we ask 1,000 people around the country whether they're voting for, one candidate or the other, we'd like to know how accurate is that sample? How accurate is the polling? If they tell us 60% go for candidate 1, then we'd like to know, is it possible that 60% of the actual people in the United States are going for candidate 1? Well, if you understand sampling, then you would know. So anyways, so our population, we are setting that there's going to be 60% oranges in our population, and then we're going to draw samples again and again. And when we draw samples, we will get varying results. Sometimes we might get 52% orange in our sample of 25. Sometimes we'll get 80%. Now, 80% should come up pretty rarely. So I'm going to go ahead and do this again and again. Now, I can make it go a little faster if I don't show the animation. So I'm going to turn the animation off, and then I'm going to draw samples again. And that went a lot faster. And I'll draw samples again and again and again. And we can see that every time we draw samples, we get different results. And by the way, the program is randomly drawing samples from the entire population. And so therefore, we expect that each sample could be a good representation of the population. Now, I have to admit, if we drew a sample of 80% and we thought that that was the true population proportion of orange Reese's Pieces, we would be mistaken. However, if we keep drawing samples again and again and again, what we'll see is that most of the results we get are pretty close to the true population proportion. Now, I'm going to speed this up by changing the number of samples. So instead of me having to click on draw samples every time, I'm just going to change this to 1,000 and get it over with, okay? And here we go. I'm going to go ahead and hit the button. Look at the histogram down here. Here we go. 3, 2, 1, go. Bam. Now, what we see is it looks like a histogram, but what it is, it's really a dot plot, but there's so many dots and they're so close together, they look like lines. Anyways, you can see that most of the results we got were in the, let's see here, it looks like here's 0.56 and here's 0.64. So between these two, these are most of the results we got. And what this is supposed to indicate is that, hey, it's possible that if we randomly choose a sample from a population, that it looks like pretty often it will be close to what the population actually thinks. Now, there are other ways. Now, we do see that there is some variance, okay? Occasionally we got as high as 80%, occasionally we got as low as 40. One thing that we can do to tweak that is we can change the size of our samples. So I'm going to go ahead and reset all this data. And I'm going to change our sample size to a bigger sample size. Let's go 50 instead of 25. So I'm going to now go ahead and draw 1,000 samples. And when I do, what I'm hopeful is that we're a little bit less spread out. Notice now we have no results in the 80% range. And we have, okay, we have none in the 80% range. We have maybe 1 out of 1,000 in the around the 42% range. But by making our sample size a little bit bigger, what we did is we made it so we have less variation. And that's exactly the technique that people use when they do polls. When you're doing political polls and you contact 1,000 people, that's why they come up with this idea that they believe their results are within plus or minus 3 or 4% of what the actual population believes. Now, later in the course, we'll get to how do they get to that exact number? How does the 1,000 relate to 3 or 4%? And what happens if you have different numbers? What if you call 10,000 people? What if you call 2,000 people? What if you call 500 people? We'll look at all that stuff later. Anyways, I wanted you to have some idea about how to use this simulator for learning about proportions and sampling. So hopefully that's a good overview, and maybe I'll give you guys some questions that you need to answer.